Welcome, folks. We're just giving it a moment for everyone to get in from the Zoom waiting room. So if you'll just give us about 20 more seconds, then we'll kick off. All right, still see folks coming in from the waiting room, so we'll just give it another moment. All right, let's go ahead and get started. So welcome everyone to this LF Energy webinar on OpenDSM, reliably measuring demand-side interventions in a solar PV world. We're privileged to have with us today Travis Sykes and Adam Shear from Recurve, who will be presenting the webinar. With that, I want to mention that if you have any questions, there is a Q&A button in the Zoom interface. Feel free to click that at any time and submit a question. If it's one we can address in writing, that will get responded to live during the webinar. If it is something that needs a little more explanation, then we'll address it after the presentation live vocally. And finally, with that, I will turn things over to Adam to kick things off.
Well, thank you so much. Yeah, and I'll go ahead and share my screen here. First, I want to say just thank you to Linux Foundation Energy. We've been part of this community now for almost a decade, and it's been very fruitful, and we've appreciated the support that LFE has offered this project and all of the open source projects that are under their umbrella right now. And very excited for today's topic. It's been literally years in the making to get to this point in this OpenDSM project. And without further ado, I'll just hop right in. So, what is OpenDSM for those of you in the audience who are uninitiated? It's very simple. It's open source, as is every project in the LFE. Methods and code for measuring energy impacts of demand side programs. So that's kind of a mouthful. Demand side program, just think of it as anything that engages a customer to change their energy consumption patterns for the benefit of themselves and for the grid and for the whole energy system, for the climate, etc. These programs have many goals. I just listed several of them. And so, why is this hard? Like, why do we need software and methods and code in order to figure out what is the change in energy consumption from something like an energy efficiency project or a demand response event? Can't you just take a look at the utility bill and say, well, last year we used 9.5 megawatt hours, this year we used 8.9 megawatt hours. So, didn't we get 0.6 megawatt hours in energy savings from that insulation upgrade that we had in our house? Well, it's not that simple. And the graph I'm showing you right here is an analysis that we did that looks at year over year changes in energy consumption as a function of the difference in temperature between the second year and the first year. And what we see is temperature alone, not to mention many other factors, is a huge driver of energy consumption within a building. So even if you had a month last year that was 2 degrees cooler than a month this year, you should expect that an average customer is going to use 5% more energy just from that 2 degree increase in temperature. If it's 5 degrees warmer, you can expect 16% higher consumption and so forth. So, temperature alone is a major driver of energy consumption, and it's something that is, of course, not attributable to a program intervention. So, we need to normalize out the impacts of temperature and other factors that we'll talk about today. So, how do we do that, and why do we do it this way, so to speak? The elements of a load impact calculation or an energy savings calculation are as follows. We have what's called a baseline period, which oftentimes is 1 year of energy consumption. So think of it as, in this case, 1 year of electricity consumption. And in that baseline period, we monitor the temperature, we monitor now the solar irradiance and so forth, and we build a model that is a reflection of how energy consumption occurred in the baseline period and what it was driven by. And in particular, we're concerned about temperature, and Travis will talk about other factors. And from that model, we can say, okay, we're going to project forward a counterfactual consumption. So I might build a model of Travis's energy consumption at his house, and then I can predict the next year of energy consumption if I know the temperature and other variables that are important to the model. But Travis might have had an energy efficiency upgrade, or he might have installed a heat pump and replaced his gas furnace, whatever it might be. And so there's an intervention that occurs, and that intervention is what we want to measure. So Travis's energy consumption changes after that intervention, and we have a difference between what we predicted his energy usage would have been, which is called a counterfactual, versus what he actually used. And the difference between those things is what we call the load impact or the savings. Now, that difference in energy consumption is something that is difficult to measure, and the production of the counterfactual itself is the subject of endless debates among evaluators and the community. So, what is the purpose of OpenDSM? It's to say, hey, we have to get out of this mode where every evaluator, every data scientist has their own way of measuring this, and we have to get to a standard set of methods that can be applied uniformly in order to establish energy efficiency, demand response, electrification, other types of demand side interventions as genuine, trusted grid resources that can compete with other supply side options. So the goal of OpenDSM is to get to a point where measuring the impacts of energy efficiency or other resources is not in and of itself a barrier to incorporating those resources as genuine competitive energy resources that can go head to head with things like a natural gas power plant. We want those two things to be viewed equivalently and trusted accordingly. So the OpenDSM timeline shows that we've really been successful actually in making this a standard across the country. And again, this is courtesy of LFE, but all the way back to 2015 and even before this project started. But I'm just going to fast forward to 2020, where we saw the some of the goals of this project really take shape. In 2020, CalTRACK, which was a method under the OpenDSM umbrella that's kind of now retired, but this whole project was known as CalTRACK for a very long time. Those CalTRACK methods were cited in the California Public Utilities Commission rulebook on governing meter-based programs. Then they were incorporated into the Department of Energy's grid meter comparison group methods. Then they were incorporated into the California Independent System Operators demand response methods. And most recently, they've been adopted as the only approved method for the for the Department of Energy for their Investment Reduction Act. I'm sorry, the Inflation Reduction Act's Hope for Homes program. So that brings us to today, where times are changing, of course, right? They always are. And those original CalTRACK methods that I mentioned are in need of an upgrade in order to handle things like building electrification, electric vehicle charging, solar PV homes. The CalTRACK methods really were not designed to handle any of these things or demand response for that matter. So for modern use cases, we need to address a number of limitations that are present in the CalTRACK methods. And I mentioned one already, they're not really built for solar PV customers. They're not configurable for demand response. And the CalTRACK methods are very kind of hardwired toward parameters that are in the model, and those parameters are upwards of 4,200 for 8,760 data points in the hourly model. That's already sort of an overstuffed model. There's not a lot we can add to it. So we actually need to free up some of the parameter space, so to speak, in order to create a more flexible modeling framework that can handle a lot of the modern use cases. CalTRACK was also computationally expensive. We'd like to reduce the burden on the users of this package. And we'd like to consolidate a lot of the open source dependencies under that OpenDSM umbrella instead of having them scattered about. And so I just have two more slides here. The features of the OpenDSM hourly model that I want to highlight, but Travis is going to get into much greater detail. Number one, they incorporate solar irradiance data in the OpenDSM hourly model now, meaning that there's a key variable that had been missing that enables better predictions of solar PV customers' energy consumption. And that is very simply how much is the sun shining? It's a variable called solar irradiance. Up until now, we haven't had that as part of the model. It is now incorporated into the model, which allows the model to be a much better predictor of solar PV customer energy consumption patterns. There's also an optimized machine learning algorithm called clustering that we've incorporated to let the computer decide based on how customers are using energy, how many distinct periods should be carved off for independent modeling, essentially. And in the previous CalTRACK model, every month was just hard coded as an independent model. That uses a lot of the parameters. It creates overfitting problems in the model. Now we have an algorithm that does that intelligently so that if a if a building just has one or two independent periods, we can identify that and we can reduce the burden of overfitting. We can use that parameter space for other more important problems that we're trying to address. Then the new model also captures intraday thermal inertia. So if it's really hot, if it's really cold, whatever it is, and that changes consumption patterns through the day, we can pick up on that now. And it can follow nonlinear temperature effects, so very cold, very hot time periods. Oftentimes, customers use energy in ways that don't follow a linear trend, and we now have the ability to model those buildings more effectively, and it's 5 times more efficient. So all of these goals are things that Travis is going to speak to. We really wanted to improve prediction for solar PV customers, meet or exceed the current performance for non-solar PV customers, reduce overfitting, make the modeling framework more extensible so we can grow and we can use it into the future, make it easier to use, make it fast. And we've done all of these things in the new OpenDSM hourly model. So this is the work of many people, many organizations over the years. One of the key things that I want to highlight today is the OpenDSM hourly model has been driven really by Travis Sykes. And so I want to give him credit where credit is due. He came in to Recurve after completing a PhD in chemical kinetics research, and we've taken that smart brain of his and we've devoted it to this problem for the last several years now. And I don't think I could have imagined where this project would ultimately go. He's the one that imagined it. He's the one that had the vision behind it, and he's the one that executed it. So congrats, Travis, just ahead of time. And I want to hand the baton to Travis now, and he can take on the actual explanation of what's going on. And so, Travis, feel free to take it away. I'll stop screen sharing.
Thank you for the kind introduction. Let me get this shared. All right. So let's start going into some details about how the hourly model works. To begin with, let's talk about what kind of potential frameworks that we investigated. So to start with, you've got your simple linear-based modeling frameworks. So you've got your linear regression, elastic net, and support vector regressor, otherwise known as SVR. Then you've got your tree-based methods, and then finally we have neural nets. Now, of these, we had to pick which one of these were likely to be most fruitful. And so we looked at linear-based methods and we said, okay, well, we're going to scratch out linear regression because it will create overfit models because we have zero feature selection. In other words, if a building is not responding to solar irradiance, for example, we would like all of the coefficients that match to that to be pushed down so that they don't affect the model. This can't accomplish that. Then we looked at SVR and we found that it was very slow, which for our purposes does not work because these models are applied to quite literally millions of buildings throughout the United States. So they need to be very performant. Then we knocked out all of the tree-based methods. And the reason why we knocked those out is because we had poor model control. Basically, the parameters that go into telling the model how it's going to work, it's just was not sufficient for our needs to be able to make sure that we were making a well-fit model and that it was not underfit or overfit. And then these methods were the tree-based methods I'm referring to were also very bad at extrapolation based upon temperature and solar irradiance. So in these models, if we decided that we were going to basically create a sub-model for January and Mondays, for example, then what happens if you fit your data and you never see a temperature above, let's say, 50 degrees Fahrenheit, but then during the reporting year, you need to predict on a temperature of that high. The tree-based methods were failing quite miserably in this regard. Finally, we actually knocked out all of the neural net methods, which might become as a surprise to many. The reason for this is because we found that they were quite expensive to run, and this is in terms of runtime, but ultimately runtime turns into dollars and how much it costs to run these models. And oddly enough, the results were not all that impressive. They were slightly better than the model that we had at the time, which I'll go ahead and point out that the only remaining model here is the elastic net. It was slightly better in terms of performance at that time, though we made improvements since then, so I would expect it to be more competitive. But it was definitely not reasonable given the cost to run. So ultimately, we selected the elastic net method. So let's dive in a little bit deeper. What is an elastic net model? An elastic net model is basically a linear regression model where you add in feature selection. So basically, that description earlier where I was saying how building is, you're giving it solar irradiance data, but it's not responding with its energy usage to that. Well, in this case, the elastic net would downweight those coefficients to 0, and then it would only rely on the time-based or temporal-based features as well as temperature. So what are the inputs into this model? Well, first of all, we have to know what the energy usage is during a baseline period or the training period. And this is an absolute necessity so that we can fit the model. This is a time series over 1 year, so 8,760 hours of data. During each of those time steps, we also need temperature, again, an absolute requirement. This is something that the previous time of week and temperature model, which was the CalTRACK model, these are the two inputs to that as well. So nothing has changed there. What has changed is this is now a fork. You cannot provide the solar irradiance or global horizontal irradiance, which is a bit more specific and technical. I might refer to it as GHI. I might refer to it as solar irradiance. Just think of them as the same thing. If you do not provide this data source, then the model will switch to a non-solar model. That way, we can basically do a drop-in replacement for the prior CalTRACK model, where the prior CalTRACK model did not require solar irradiance, and in many cases, it's either unnecessary to run solar irradiance if you know that your customers do not have any kind of solar panel system on their building, or if you're unable to acquire the solar irradiance data, or if you are able to provide this data, then it swaps to a solar model where it will you could apply this to non-solar buildings, and if they have a response to the solar irradiance, you'll see a benefit, and if they don't, or if they do, if they do respond, you will see a benefit, and if they don't, it'll be downweighted to where it doesn't matter. And then finally, this is a big change here. Previously, the model that we had, which was the CalTRACK model, was incapable of being easily extensible to additional supplemental data. I'm not going to say that it was impossible, but it would have been difficult. Now, we have made this very simple. if you are in kind of a research and development state where you're trying to determine if a new parameter would impact the model in a positive way, you can use this, put that in as supplemental data and do the test yourself. So this is an optional and an experimental feature. I say this because this supplemental data is not advised to be used for making actual measurements, because there's no way for us, the creators of the model, to know all of the potential supplemental data that a person might input and say, yes, you can trust this. In terms of the output, you put all of that into the model, you will get an output. And the output is going to either be the baseline model or the counterfactual within the reporting period. Going a little bit deeper, we have changed the model so that it will fit and predict on 24 hours, aka 1 day. The reason why we did this, Adam alluded to earlier, is so that we can inherently capture thermal inertia without having to do anything special. So day to day, parameters tend to be somewhat correlated with each other. So if you have a high temperature 1 day, it's likely that you will have a high temperature the next day, not necessarily. So you could argue that this does actually capture somewhat of the thermal inertia between days, but most certainly within a day, we are capturing those effects. And days are generally, going into the model, are time zone sensitive, and therefore they are starting in the middle of the night and ending in the middle of the night. So the middle of the day, when the greatest change is happening, you see many hours before that. Now, let's back out a little bit. We've already talked about this a little bit, but let's just think about how models change behavior in general. So first of all, it's time-based, or temporal, based on hour of the day, day of the week, month of the year. So the way that we approach this is we create unique bins based upon the day of the week and the month. And again, every single day is being predicted 24 hours. So 24, the hour is already inherently within this. Then we have temperatures, where if a building is likely to use slightly less energy during moderate temperature than it is during an extreme temperatures, so whether that be very cold or very hot. And because of this, we create unique bins based upon the temperature. Then if you have a solar PV system on your house or on the building that you're measuring, clearly solar irradiance is going to be a key parameter here. And so we need to include GHI, or solar irradiance. Then, due to the structure and how the model is formulated, it is an absolute necessity that we impute or interpolate any missing data, because of the structure of being 24 hours, if one of those hours is missing, it's could cause very detrimental effects to the model. We have introduced, I'll go into a little bit more detail. It's the way that the code is actually structured is that we have a data class where it handles all of the imputing, the making sure that you have enough data so that you can actually create a valid model, and all of that gets put into the model class. So you, as the user, do not have to worry about any of this imputing or interpolation. That is more of the OpenDSM's problem. And then finally, for anyone who's actually looked at hourly data, I'm sure that you're well aware, but for those that have not, some hours are just weird. People's energy usage is based upon how people use energy, not just about how the building uses energy, which means that if you decide that you want to try your hand at blacksmithing, you might be heating up a forge or something of that nature, and the amount of energy usage that you have will skyrocket. Or you might go on vacation, and for a couple of days, which is unusual, your energy usage basically drops to zero. So due to these weird things that can happen, we have adaptive hour of day weighting. Again, we're going to peel the onion and go one level deeper. So let's talk about the temperature binning. Up here at the top, I show these are the actual bins that we use. So that is 10 degrees, 30 degrees, 50, so forth. All of these, the model is built to work in Fahrenheit. If you're using Celsius, convert your units accordingly. But the way that this works is we have a low temperature, which is the last bin that actually has data. And we have a high temperature bin, which is the highest temperature bin that actually has data. And everything else, it's kind of a middle, moderate temperature. Now, for those middle moderate temperatures, it's we basically treat these as linear. And I should also back up and mention that these exact temperature bins are specified. They are not something that changes. Though during the process of creating this model, we did look at many different types of bins and how to structure these. And this was ultimately the bins that came out to be the best and the most performant. So this is not by accident. And within these bins, all of them have linear behavior, which is to say, within each bin, the response to temperature has a unique intercept and a unique slope. Now, again, because buildings can be weird, and it is most likely that they are going to be weird at very high temperatures and very low temperatures, we actually treat those bins differently. So at the extreme temperature bins, we have some non-linear effects that can get added in. Now, again, I really want to emphasize this nonlinear behavior is currently set up to only function within the lowest and highest temperature bins. Now, let's think about why a building might be weird in these temperature bins. So first, let's talk about high temperature and an AC usage. So with an AC, if you get up to very high temperatures, there's a couple of circumstances that could happen. First is you might decide that you don't want to spend that amount of money on cooling your house, and so you raise your set point, in which case your energy usage might actually decrease. And this would likely be, you would further decrease it as temperature goes on because you're wanting to save money and make sure that you don't exceed a certain budget. Or another thing that could happen is that your AC unit saturates. It can no longer cool the house, and so it will kind of reach a steady state of and tail off to where it just is it's a flat amount of energy that it's using. Or your AC unit could just continue pumping away and cooling your house, in which case it's going to require more and more energy as the temperature outside increases, in which case you would have an increase beyond a linear increase. We could also say that like at the low end, similar things could happen. If let's say you do not have electric heating and you're measuring electric data, in that case, it would just drop off precipitously. And because you are now switching over to a gas system to heat your home, and so that part of energy would be on a different form of energy, not electricity. Or it could increase because you are heating your home with electric usage, or same as before, maybe you're trying to meet a budget. You set it so that you will not exceed a certain amount of usage per degree that you're lower, where things flatline. This basically describes all of that. So here, this plot that I'm showing is a normalized response on the Y and standardized temperature on X. And the whole point of this is basically just to show that all of the different circumstances that I described can be accommodated with this system. So this is 3 different data streams that are fed to the model, and the model will apply a coefficient to each of these. So you could actually come up with some pretty complicated combination of these three things between the linear response, the negative exponential response, and the positive exponential response. And so all of this is to help us describe the very complicated and diverse set of conditions that can happen during those extreme temperatures. I should also mention, by the way, the hardest part about creating this model, it's not hard to model an individual house. It's very difficult to create a model that is abstract enough to model any house or any building. That's the real difficulty here. Now let's move on to temporal clustering. So I had said that we used day of the week and month of the year. Now, if you do a full factorial or all of the possible permutations of the day of the week and the month, you end up with, I think it's 82, 84 combinations, which is likely to give us a rather overfit model. So it's too many combinations. We wanted to reduce that down. So what we do instead is we create clusters of the days of the week and the month combinations that behave similarly to each other. Think of this. I'm actually going to skip most of the really deep details here, just because I think that it's easier to explain all of this by looking at plots and an example. So let's think about a small retail store where at this mom and pop store, of course, they've got to stay open during the weekends. That's when they're getting the most business. But they want to have some time off, so they decide they're going to shut their store down during Wednesdays. Well, this is not a common thing to do. A Wednesday would be an unusual day to shut your store down, but it's possible. And with this system that we have set up, we can detect that. In fact, this is not even a hypothetical situation that I'm describing right here. This is an actual situation. So this is what I'm showing here is energy on the y-axis and hour of day on the x-axis. And then at the bottom here, we show the combination of the month and the day, and it aligns so that you can see which day applies to, or which combination applies to which cluster. And here you can see this starts on Monday. So we've got Monday, Tuesday, Wednesday is a different cluster. And again, 3, 3, 3, 3. Every Wednesday, they switch to this cluster here, where they basically shut down all usage. And then you can see that the building has normal usage during the rest of the days of the week. Now, for this procedure, we can, it's not just that we capture this. We didn't tailor the technology to just capture Wednesdays. We captured it so that we could capture any number of combination of things. So perhaps the more normal usage that one might expect would be weekdays, one usage, weekends, another usage. And this is an example of that. Here, the weekends is shown in purple and the weekdays is shown in green. And here you can see that the weekdays has slightly more usage than the weekends, as well as slightly different curvature and behavior and so forth. And this is something that we detect and that we decide, or not we, I say we, speaking for the model, but the model detects and the model will say these clusters are behaving similarly. They should be separate. So far, I've only shown examples with 2 clusters. This is not the maximum that we can do. It's far from it. Here's another example with 3 clusters. So in this one, Sundays are different. Each Sunday is here in purple. And then it looks like we have winters are separate by themselves in cluster 2. And cluster 3 is showing more of the spring, summer, fall. Another possibility here is that we could actually be looking at daylight savings time, which would be something that would be fantastic if we were able to detect and create a new model specifically for daylight savings time, when that 1 hour shift could make a difference in how you're using your energy. I would also point out here that, yes, I have shown a limited number of clusters, 2 and 3 now. The reason for this is simply for us to understand what's going on. In reality, the model can select up to 24 unique clusters for the 84 possible combinations. So that way, we are shrinking down the potential number of models that we would need to create, or the number of coefficients, but it's still rather high and able to capture basically anything that we've been able to throw at it. Excuse me for just a moment. All right. So how do we actually apply all of these things together? Well, what I've described so far are temperatures and temperature bindings and temporal clusters. Well, in reality, what we do is we apply all of these together and we look at the interaction between all of them. So here in this top plot, I'm showing the usage components, and in the bottom, the usage total versus temperature. So what we do is, let's say that we have a meter where we have 2 clusters. One is the weekend and one is the weekday. So for such a meter or building, what we would do is we would have a common global temperature response. So if you were to add nothing else to this building, both the weekend and the weekday have this kind of general usage. But we also have a modifier on top of that global response for the weekend and the weekday. So for the weekend, it's basically flat. It matches whatever the global response is with a slight offset, and then it has a decreased usage followed by a further decreased usage. Now, this is how the model is working under the hood. You wouldn't see that. In fact, a little bit closer to what you would see would be here at the bottom, which is the combination of the weekday and the global and the weekend and the global, where temperature rises and usage increases. Once they hit about 90, this house decides, or this building decides, that they don't like being hot, so they're going to increase their AC usage. So it increases even further until they hit 105 degrees, in which case they decide that they can't afford to continue cooling their house to that degree, so they raise their set point. Versus the weekend, perhaps this building is a commercial building only open during the weekdays. Well, at that point, they want to keep things cool, but once they hit 90 degrees, they care a little bit less until they hit 105, and they just say, we're done. We're not even going to try. We'll worry about it on Monday. And the usage just drops to 0. This is a hypothetical situation. I'm sure that I could probably find a building that follows this. But the point here is that you can imagine many different situations in which a building responds to temperature and time of the week and month, where all of this comes into effect and matters a great deal. One little caveat, if you're wondering why we have a global response, the reason for that is, and this gets into kind of a little bit of model details, is that there is a possibility that if we were to only have weekend and weekday, that we would not have a value for the weekend in which the model is actually fit. So instead, we say, well, what if we just have a global response and then a modifier on top of that, which is so that the model always gives back some kind of a reasonable response, even if it's not the best response if you're missing data in the weekday or weekend from the fitting time period. All right. Now, next is the solar PV production, which is surprisingly one of the easy parts of this model, which is kind of funny to say, since that is one of the primary motivations to this model. But well, we know that PV production is proportional to GHI. If you have more sunlight outside, you will get more energy from your solar panels up until you hit saturation. And so basically we can treat GHI, we put that into the model, so solar irradiance, we put that into the model, and we just say this building is going to respond linearly to that GHI based on the number of solar panels that you have, and the amount of production that you have will increase that. And that is the response that you have to PV production. So it's honestly rather simple. In terms of the supplemental data that I brought up before, again, we treat this as linear. And we have to do this because we don't know what people are going to put into supplemental data. It also has to be complete. So we will interpolate or impute, however it depends on what part of the algorithm it reaches, on which of these is accurate to say, but we do not impute the supplemental data as we do impute the PV production, the GHI, and the temperature. So this has to be complete if you're going to be using this feature. Finally, we have the downweighting that I described earlier. And the whole point of this is to reduce the effect of influential outliers. Here on the right, I show a plot. It's just a generic plot of, let's imagine that you have a flat line model to describe what's going on here, and then you have this one data point. If you have outlier rejection or downweighting, the model will be pulled down to the bulk of the data as opposed to being pulled up quite significantly, and it would no longer represent normal usage. So basically, what we're trying to say is we want the model to predict normal behavior, because we have found through our population results that basically using this outlier downweighting creates the most predictive models. In other words, we don't want to predict what happened last year. We want to predict the normal usage of last year. And it's an important critical detail here, because these models are used to predict a time period that you cannot see, that does not necessarily reflect the training period. So the best that we can do is to predict normal behavior. We also have shown that this does not introduce bias, and each hour of the day is treated independently. And that's because different hours have different varying amounts of variance or scatter. So middle of the night might be a little bit less variance than middle of the day. And so we want to make sure that we downweight things appropriately for the hour of the day. All right, that has been a lot. That is a summation of how this model works in broad detail. The next thing is, all of that is great. Nice words, nice thoughts. Show me how it works. Does it actually work? Let's go into it. Let's start with the model goals. Improve solar PV production, meet the accuracy of the prior model, which another way to put this is do no harm, since we're replacing the prior model. 3, decrease the overfit, because as Adam mentioned, having those 4,200 potential parameters, it's likely that the old model was pretty overfit. So can we fix that? 4 is to add those R&D features so that we can allow arbitrary inputs or supplemental data, as I called it. 5, we want this to be easy to use. It can be as complicated as need be under the hood, but the user should never have to deal with that. It should be very easy to use. And 6, we want it to be fast. Now, of these, if we can only answer 3 of these with population results, which are, did we improve the solar PV prediction? Did we do no harm? And did we decrease overfit? Let's start by talking about the first 2. To begin with all of this, let's just say that this is a pretty extensive set of data that we tested all of this on, and that we fit and so forth. It is 33,000 residential and commercial non-participant meters, all from the MCE service territory, which is California Bay Area and North Coast regions. We used 3 years of data ending in March 1st of 2020. And this is a full breakdown of all of the meters. But for our purposes, and during this talk at least, I'm only going to be focusing on the residential non-solar and the commercial non-solar customers. If you're interested in more, please visit our website at opendsm.energy, where you can find the full report with many more details than I'm able to go over during this time period. To start with, let's talk about the non-solar customers. Basically, this is 4 panels. Each panel is showing frequency. The left 2 panels are showing CVRMSE annual improvement, which, if you're unfamiliar with CVRMSE this is the RMSE of the model on an annual basis divided by the average usage of the meter. So this way we can treat all meters the same. Now, on the right 2, I show NMBE, which is the normalized mean bias error. And this is kind of a similar correction in terms of divide by the mean usage, but instead that's applied to bias. And the top 2 are residential, bottom 2 are commercial. That's a lot of detail to go into for a rather simple set of data. Basically, we see a 1.2, 1.23 increase it is better for the residential CVRMSE, 1% worse. If this were me, if the model is 1% difference and it's back and forth like this, I say it's a wash. The model is basically the same. We see basically the same thing for bias, in that we are not significantly biased in one direction or the other. So again, this basically answers the question of, have we done no harm? Correct. We've met that goal. Now let's talk about overfit. So here I'm showing the overfit score, which is the reporting RMSE divided by the baseline RMSE minus 1. Residential at the top, commercial at the bottom. If we had a perfectly fit model, we would be at 0. That's the thing to note here. And what we are seeing is that the overfit score is improving by about 25% from between the legacy model or CalTRACK model and both the non-solar and the solar models. So we are doing a better job in terms of improving the amount of overfit that we are using or generating. This is really important. Why is this important? Because we use our error metrics, one, to decide whether or not a building can be modeled or should be modeled and measured using this methodology. So if the baseline is not reflective of the reporting period, for example, then you might be allowing buildings into your portfolio that should not be measured because their error is too high. It's just that that error is not being represented properly. Also, this is particularly helpful because what is a measurement if you do not provide uncertainty? And what value is uncertainty if you can't trust the uncertainty? So previously, the uncertainty was always underrepresented to what it was. And while the same could be said for the current model, it's not something that can be argued that we are doing a better job of that. So this is important, but it does have some fine details here. Now, all of this is done on an annual basis. So let's jump into the weekdays and weekends and on an hourly basis, because this is the hourly model and we care about these things. I apologize. I do have to speed up. So this is going to go a little bit faster. Here, I'm showing the baseline error on the top, reporting error on the bottom. Summer, this is for the hour of the week, for the summer, the shoulder, and the winter. The thing to note here is what I just showed you doesn't even represent how much better we are doing for the amount of overfit compared to what we're seeing here. I should also mention this is non-solar commercial. The blue represents legacy. And what I'd want you to look at is that the error profile that we're seeing for the legacy model doesn't really represent what we're seeing in the reporting period. And we don't normally have the reporting period because that's what we're trying to measure. All we have is the baseline. So we have to assume that the error is going to be similar between the baseline and the reporting period. But with CalTRACK model, it's just not in many cases. Whereas if you just squint your eyes and look at the new OpenDSM model, you can see that actually, yeah, the error is very similar. There's a couple of areas where there is some discrepancies, but overall, it's doing a fantastic job between predicting what the error would be in the baseline and transferring that to the reporting period. So again, we have made huge progress here. Now let's jump into talking about the solar information and how solar predictions. Well, before we start any of that, we actually need to talk about those normalized error metrics a little bit, because CVRMSE is not a metric where we can judge a solar meter. When you set up a solar PV system for your home, for example, it is very likely that you set up that system so that you meet the annual usage of your household's consumption, which is to say, if you look at the total, at the average usage over the entire year, you are purposely designing your system for that to be as close to zero as possible. Which, what does that do to CVRMSE? Well, now you're dividing RMSE by a value that you are purposely trying to make as close to zero as possible, which means that CVRMSE is going to blow up. So if you have a sufficiency criteria that says you cannot be above 1.4 CVRMSE, well, you may as well just start eliminating solar PV customers because they aren't going to meet that criteria. So instead, what we've done is we have introduced PNRMSE, which is percentile normalized RMSE, where instead of normalizing by the mean, we're normalizing by the IQR of the observed data, or the interquartile range, which is a measure of the variance of the data. So now we're saying, what is the error relative to the variance of the observed data? This is something that will always be positive, even for solar customers. So this is something that we can use to reject customers, or sorry, qualify or disqualify customers based upon. Now, we don't want to remove customers which we had prior. So what we've done is we've actually made this a permissive system where you can either be qualified based off of the meter's CVRMSE or the PNRMSE. So the goal here is just to add more customer and be modeled. And if you're interested in how PNRMSE and CVRMSE are correlated, here's a plot. And currently, we did choose the PNRMSE threshold based upon CVRMSE's threshold at 1.4. This is something that we will likely want to come back to later. But this is a conservative estimation of what these values should be at this time. Okay. Now we hit the key plots of this presentation, which are how are we doing on solar customers. So this is solar residential. The top plot here is PNMBE, so we're normalizing the mean bias error by the IQR, and this is the mean PNRMSE for these customers. And the x-axis here shows the mean irradiance loss, which is how well do we do when it's sunny versus cloudy. So on the left here is very sunny, and on the right is very cloudy. And basically, for PNMBE, the goal is to be as close to zero as possible. And you can see that for the new solar model, which is the orange, we're doing significantly better in terms of bias than we were with the legacy model, particularly as you get to cloudier and cloudier days. And the reason for this is because the old CalTRACK model may have been perfectly fine on an annual basis for solar production. And the reason for that is because year to year, the amount of solar irradiance that you get over the entire year doesn't change all that much. But what matters is when we're talking about individual hours or time periods within that year, in which case CalTRACK can't be trusted. It's just not going to give you the correct answer because most of the year is sunny. So it's doing a good job during those time periods. But then you get to the cloudy periods and CalTRACK's just completely biased because it can't see that there's a cloudy time period. It just knows what it did roughly during the entire year, whereas now we can. Now we also do, for PNRMSE, we would want to be as close to zero as possible, and you can see this is just a net win. We have done it. It is lower in all instances, which means that our error is better during all periods of the time for residential customers. For solar customers, same story, except it's actually even more extreme, where we are even closer to 0 in terms of bias with the new model, and CalTRACK is even further off. Now, during sunny periods, we're roughly equal to CalTRACK, but once you hit those cloudy periods of time for PNRMSE, again, nothing but improvement. So did we meet our goal of making a better model for solar customers? Yes. What we have done is effectively de-risk and make it so that you can trust results on an hour-by-hour basis. So overall, we believe that the new hourly model is a success. We have improved solar PV prediction with no caveats. We have met the accuracy of the prior model on non-solar meters. There is a slight caveat here in which there is a slight difference on weekends versus weekdays, which I didn't get a whole lot of time to go into detail on, but we are slightly worse during weekends, though we're better or equal on weekdays. It was decided that this was acceptable because there is actually a link between how overfit we are and how well we do on weekends. And it was decided that it was better to be less overfit than to try to fit those weekend meters perfectly. We have decreased the overfit without question. We have created R&D features to allow, or the framework to allow R&D features is done. I guess the fit number 5 is a bit subjective, but I would argue that it is significantly easier to use with the new API, and we have most definitely made it faster because it is 5 times faster than the prior model. Work does not end, so the next thing that we're going to be working on is making a DR model. Everything I just described is an EE model, energy efficiency. We're going to make a demand response model, and we're going to be using the model that I've described today as the foundation for that demand response model. We also would like to look at all of our sufficiency and just do a complete overhaul and see if we're too conservative, which I think is almost certainly the case. Can we make it so that we can increase the number of buildings that we allow to be measured? Another huge initiative that we've been working on is to completely overhaul all of our documentation. So please, if you are interested in using these models, visit opendsm.energy, where here we lay out the methodology. You can look at all of the sufficiency criteria. You can see examples of how to use this code as well as API reference material, and also the much longer reports that, again, I'm only giving you a piece of today, are all within the references section. So you can look at those reports yourself. With that, thank you all for coming today. And if there are any remaining questions, we have 2 short minutes to answer them.
As of right now, all the questions were addressed in text, but if there is a last minute question, we have a minute here. All right, well, seeing none, thank you again to our panelists for presenting today. And thank you to all of our attendees for coming. We will be sharing the video and the slides of this in the next day or so.
Thank you all.
Very much.
Thank you, everyone.